What you are seeing here is an online multiplayer game of Ultimate Tic-Tac-Toe being played on a Nintendo 64.
Now, I know Tic-Tac-Toe isn't really the most exciting game ever, but I do think the technology on display is worth talking about. Flashcards are a popular tool for bringing your old consoles back to life, and something that a few flashcards have is a USB port, which allows you to plug the cart to the PC for debugging purposes. So my idea was to leverage the fact that a PC can connect to the internet to allow people to play multiplayer games using a flashcard. Now, this isn't the first time you could connect an N64 to the internet. During the console's lifespan, if you were in Japan, you could have gotten a game called Morita Shogi 64, which was a shogi game that the cartridge had a little modem port on top, which would allow the user to connect to game servers. Or if you owned an N64DD, you could have gotten the RandNet disc, which featured a modem cart, which would allow you to connect to what was essentially just a really fancy web browser that you had to pay a subscription for. Now, I've split this video into two parts. The first is for people who don't really care about the technical details and just want to know what they can and can't do right now. And the second half is for the more nerdy technical detail breakdown of how all of this works. Timestamps are over here and the video description. So, you will need three things: a Nintendo 64, obviously, a computer with either Windows, Mac, or Linux, and a flash card with a USB port. As of this video, the only flash cards I support are these ones, and the reason for that is that these are popular enough that I can find technically minded people to help me test with them. There's also some flash cards on the market which claim to have USB support, but then half of them don't even have the USB chip soldered on the PCB. These cards don't even have any documentation on their USB interface, so I literally cannot support them. If you fulfill these requirements, then head over to the Netlib GitHub page linked down here and in the video description. And then head over to the releases section over here on the right. Download the Netlib browser zip for your operating system. In my case, I'm using Linux, so I'm going to download the Netlib browser Linux zip file. Make sure you fulfill the system requirements. Those are explained here in this big README in the section aptly named System Requirements. In my case, I'm on Linux, so I'll have to fulfill these requirements over here. It's telling me that I have to run this included installer script that's inside of the zip file. If you're on Windows, you'll have to download this driver that's linked over here. And if you're on macOS, you'll have to follow the instructions that are over here that I can't really explain since I don't use macOS. Alright, so once this zip file is downloaded, extract the Netlib browser to your preferred location. I'm going to move it to a folder on my desktop and then double click it to run it. And you should see some servers. As it is right now, there's 3 servers up. And these servers are just showing the example ROMs that are in the GitHub repository. Hello World is just a very basic Hello World for your N64. Real Time is a real-time multiplayer game example. And Tic-Tac-Toe is the example Tic-Tac-Toe game that I showed in the beginning of this video. Now, depending on which flashcard you own, this next step is a little different. If you own an EverDrive, you'll need to plug in the USB, and you'll need to have the console turned on and in the EverDrive menu. If you own the other cartridges, you'll have to have the USB plugged in and the console turned off. When you've done that, you are ready to join the server. So just double click on the server that you want to join. In my case, I want to join the Tic-Tac-Toe server, and it's going to ask me if I want to download the ROM, so I'm just going to click yes, and we'll let it download. Once this finishes, a little window should pop up telling us that we are ready to connect. And it's saying over here, you may now boot the console. So I should now be able to safely boot the console, and we are now in the game lobby, so we can start playing as soon as someone else joins us. Now, if the server that you want to join happens to be full, well, you can just host your own. On the GitHub repository, go to the examples section and look for the game that you want to run. In this case, let's say I want to run the Tic-Tac-Toe game. Go to server, and over here there are instructions on how to run the game server. You'll need to make sure that you're port forwarded in order for other people to be able to connect to you, or to make sure that universal plug and play is enabled on your router. If you're not sure what either of those things mean, well, then you'll have to search it up on Google because it depends on your router. Once you've created your server, your friends should be able to join you by going to the File Manual Connect button over here and putting in the server IP and the port. and then giving the path to the ROM. Or if you've allowed your server to register itself to the master server, then it should show up here as soon as someone clicks the refresh button if they weren't already in the browser. If they were already in the browser. Now, if you are a developer and you wish to contribute your own games to the library, then make sure you read through all the source code that's in these examples because it is thoroughly documented. But I have also created a GitHub Wiki article that covers everything you need to know about the networking library and about multiplayer game development. So you might say, these games are boring. Can I use this to play Super Zelda Racing? And the answer is, perhaps in the future. I very much just released this project, so it might take some time for people to start developing stuff for it. And that's if people even want to begin with. N64 development is already difficult enough, and having to make multiplayer stuff brings a whole new list of challenges. Games need to be designed specifically for multiplayer. It's not something you can just drag and drop. So if I wanted to, for instance, take a single-player game that already exists and turn it into a multiplayer one, that might require rewriting huge portions of the game. If you want to understand why, well then stick around because we're going to get to nerdy technical details about multiplayer game development.
Multiplayer games come in two main formats, peer-to-peer and client-server. In a peer-to-peer system, players are keeping track of all information of the game at all times. For this to be possible, a lot of work needs to be done in synchronizing the game state between players. For instance, if a player presses the A button, this data is sent over the wire, and the game will not detect this input until all the players receive this information and agree that the button was pressed. Otherwise, the two games would go out of sync. This isn't very ideal for most multiplayer games because it means that the player with the slowest connection holds everyone back. But at least everyone is able to agree on what state the game world is in at all times. Another problem is that it can be difficult to prevent cheating. Since all players need to be completely synchronized, that means that players will require access to information they should probably not have. So, games tend to opt for the client-server model. Instead, we have a central server that is running the game, and clients, which are players, all connect to the same server. This server is the arbiter who decides what is right and wrong, and is able to decide what information clients are privy to. Clients run their own version of the game and periodically tell the server what is going on in their own game. The server will then validate this information and send it to everyone else if necessary. To communicate over the internet, there are two main networking protocols: TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. Without getting into the specifics of the implementations, TCP offers reliability while UDP doesn't. Packets sent over the internet might arrive to their destination out of order or might not even arrive at all. So TCP will buffer packets to ensure everything arrives exactly as it was intended. Unfortunately, this makes TCP unsuitable for real-time games. Not so much for turn-based games though, because speed is traded off for reliability. In a real-time game, packet reliability is not as important. For example, if a game is constantly telling you the current position of a player, it doesn't really matter if you receive an old packet or you don't receive anything for a few milliseconds, because you are going to receive a more up-to-date player position packet in the very near future. However, we might need to send packets that absolutely cannot get lost, so we need to implement a simple reliability layer over UDP. One simple solution for this is every time we receive a packet, we respond with an acknowledgement. If an acknowledgement is never received on the other side, then it can be assumed that something got lost and the packet can be sent again. This can work fine, but it's a bit inefficient because we're spending half of our bandwidth just sending acknowledgements back and forth. Instead, we can leverage the fact that both the client and the server are going to be transferring data back and forth to buffer our acknowledgements and send them along with whatever data we actually want to send. One way to do this is to assign each packet a unique number, and every time we send a packet, we increment this number. We can keep track of identifiers in the packets we received from the other connection, and then when we send our packet, we can just include the list of the last numbers that we received since this packet. One of the benefits of this is that if one of the packets we transmit gets lost, the next packet we send will still contain all the previous acknowledgements. And when we get a reply back, we will spot that the other side missed the packet and we can just resend it. If the packet wasn't actually lost, but rather it arrived late and the other side has already sent us a replica because it assumed it was lost, we can just check that number exists in our list and ignore it if so. One of the annoying things about networking is that the larger your packet, the easier it is for it to get lost. In UDP, it's recommended to keep packets smaller than 4 kilobytes, and having to send acknowledgements for a bunch of packets can unnecessarily eat up our size budget. So one of the optimizations we can do to compress the acknowledgement data is to leverage the fact that these numbers are in sequence. We can choose only to explicitly include the last largest number we received, and then have a bit field that represents the previous numbers we got. 1 for a packet was received, 0 for not. Of course, one of the nuances of a bit field is that we can only represent so many numbers in the past, and if we go enough packets without receiving an acknowledgement, that packet is lost forever. In my networking library, my bit field is 16 bits, so you can receive up to 17 new packets without an acknowledgement before we can consider the packet lost. Another issue is that we need to be able to handle overflow. Since I am using 16-bit sequence numbers, once I try to go higher than 65,535, that will increment to 0. So it's important to be aware that the 0 is actually a larger sequence number than the previous one. Now, it obviously doesn't make sense to do all this stuff on the N64, which is why I don't. I leverage the fact that the N64 needs to be plugged into a PC to just do all the packet handling logic on the PC, and then I send to the N64 only the relevant data, which also means less load on the slower USB of some flashcards. In the current version of the library, I simply do not support packets larger than 4 kilobytes, but supporting that in the future is not very difficult. I can compress the data payloads to keep the packets small, but if I really cannot avoid sending a large amount of data, I can just split the packet into chunks and then send them in parts. Another tricky thing that I haven't implemented just yet is congestion avoidance. If I send too many packets too quickly, the router will slow down the traffic to avoid getting overloaded. So network handlers tend to implement some algorithms to send out packets at a reduced rate if it feels that the user's network is congested or slow, and it'll speed it back up once the clients are stable again. Since the example games I wrote require such little bandwidth, I opted to implement this feature later if someone has a need for it. So with all of that out of the way, making a turn-based multiplayer game is relatively trivial because the server can reliably and quickly broadcast the game state between players, and the server can choose exactly what information a client can see. However, if you want to make a real-time game, this is quite a bit more complicated for 2 reasons: synchronization and cheaters. We'll start with the first one. In a video about my N64 game dev series, I talked about tick rates in game engines and how they are used to ensure a game's physics always runs at the same speed regardless of frame rate or how fast the processor is. If you're unfamiliar with this, I recommend checking that video out for an explanation. It's important that the server use a tick system because without one, it will update the game state really quickly every second, which means you will need to send these updates to every client, which costs a lot in terms of bandwidth, not to mention it will flood their connection. Using a slower and more relaxed update system is a better idea. Quake 3 and Unreal Tournament, for instance, both use a default tick rate of 20 Hz. Not only is it good for the connection, but it's also good for the client. Typically, our games will be running at a much higher frame rate than the tick rate. So if our client is simulating the world much faster or much slower than the server, the two will quickly go out of sync. Using a tick system does have a drawback which we will need to work around. But first, I'd like to discuss the second topic of cheating. One of the major rules of game networking is that you should never trust the client. For instance, if we calculate the position of our player character in the client, and then the server just blindly believes what we tell them, nothing is stopping us from just incorrectly calculating the player's position to somewhere a little bit more convenient. So instead, we only allow clients to tell the server what actions they took, like what buttons were pressed, and then the server will calculate the player's new state and send it back to them, and obviously everyone else in the game. There is one small problem with this, which is that the player will only see this new position after the time it has taken for the packet to travel to the server and back, which could be in the hundreds of milliseconds if the connection is weak. So your input will feel very delayed. Fortunately though, most clients aren't cheaters. So what we can do in the client is predict where the server is going to tell us the final position is by just doing the physics calculations that the server will do on the client. Even if the client cheats and calculates an incorrect prediction, it won't matter, because once the server's response arrives, they'll just have their position corrected. And if the client chooses to ignore the correction, well, that's a them problem, because their actions won't sync up with the server, and thus won't affect anyone else, since the server is the final arbiter of truth. There is a problem with prediction though, which is by the time a tick has passed in the server and we receive an update packet, we could have predicted many frames ahead. And thus, when we receive the packet telling us where we're supposed to be, we will teleport back to where we were when the packet was originally sent. This sort of rubber banding is not ideal. So there is a second improvement that we can apply on top, known as reconciliation. The idea behind this is that when we send the server our inputs, we keep them stored in memory. Once the server replies back with our corrected position, it also sends the timestamp of that position. What we can do now is when we apply the player's position, we look at all the inputs we have stored since, delete the ones with older timestamps, and we can reapply all the inputs that happened after that timestamp. Now, in order for us to send timestamps, we need to have our client's clock synchronized with the server's. When I say clock, I don't mean like a real-time digital clock, but rather just some number value that we can use to keep track of happenings during gameplay, like for instance the exact time a player shoots. This is tricky because if we ask the server for its current time, when the response packet arrives to us, it will already be out of date. The best thing to do here is to send multiple requests, at least 5 should be enough, and then we calculate the return trip time, which is the time it took for us to receive a response, and then we add the average latency to the last clock value we got from the server. It won't be perfect, but it will be good enough. It's typically a good idea to keep performing this syncing algorithm periodically during gameplay to ensure that the client's clock doesn't deviate for whatever reason. Using both of these algorithms, we have completely made the player's own movement smooth. But we still need to fix the fact that other objects in the game aren't moving smoothly. The algorithms we applied for the client work because we know what we, the player, are doing all the time. But we have no way of knowing what other players are doing until we receive another packet with that information. For instance, if the other player was walking forwards, we could predict this movement easily. But we wouldn't know that they actually turned right until that packet arrives. And once it does, well, you'll get rubber banding. So the solution here is to delay everything that the player sees on the screen by a few ticks. Like that, we always have correct data to sample from to fill in the gaps between the ticks. Like I said in the previous video, you might say, wait, doesn't that mean that what I see on the screen isn't really what's happening in the world simulation and is technically a few subticks behind reality?
Well, let me let you in on a little secret.
Modern games, especially multiplayer games, already do this all the time, and you probably haven't noticed.
Now, there's still one big issue that needs to be solved. For instance, if the player shoots a moving target, by the time this packet arrives at the server, said target will be long gone from this position, meaning that the server will tell the client that they missed, despite the fact that they didn't on their own screen. The only way to solve this is by the server keeping track of the positions of all objects in the past. Like this, when the client sends the shoot packet, they also send the timestamp of the shot. When the server receives this packet, it will use the timestamp to verify the object's past positions to confirm whether or not it was actually there at the timestamp the client claims. If it turns out to be true, then the server notifies everyone involved about the successful shot. Remember, the server should not just blindly trust the client that the shot landed, because our client could be cheating. Most game servers only tend to keep a second or two of past positions. Any more than that would be unfair and open to exploitation. I mentioned that one of the big downsides of peer-to-peer games is that the clients need to keep track of everything, since the game state needs to be synced between all players. This makes writing something like a wall hack trivial. One of the benefits of the client-server model is that the server only needs to send to the player whatever information it deems necessary. For instance, if this was a single-player game and all the other characters are bots, the game will need to keep all of this in memory and perform AI logic for everyone every tick. In the client-server model, the server would be the one doing all the calculations, and then it'll just tell the clients the results. But even better, if the server avoids telling the player about what is happening in parts of the map that they can't see, that's less data to send over the wire and less data that the player has access to that they probably shouldn't. Unfortunately, you can't completely protect against wall hacking. For instance, the server can choose not to tell the player about this enemy ahead of time, but if the player peeks the spot, by the time the server is aware that the player did this and the packet that tells us the enemy is there arrives, the player should have already seen this enemy a long time ago. In this scenario, the enemy will just suddenly pop into view, which is not ideal. So, despite not being able to see this enemy, the server needs to tell the player ahead of time, because both players' actions are unpredictable. Cheating in real-time multiplayer games is unfortunately something that is impossible to resolve without forcing the players to compete in completely locked down systems. A company can create an insanely invasive anti-cheat software, but such a thing can be bypassed by an Arduino because ultimately the user still has access to their own hardware. The best approach for handling cheaters in a multiplayer game is by using heuristics, machine learning, and an honor system in the server itself to deduce whether or not a player is acting suspicious. Of course, if a cheater is subtle enough about how they cheat, they will probably never get caught. Like I said, it's impossible to solve without limiting the player's hardware.
And that's all I really wanted to talk about. Like I said, this library was just released, so you can't expect many games right now. But hopefully we can start seeing some homebrew which makes use of the library in the future. Regardless, I hope this video has been useful in demystifying how multiplayer games work, and if you enjoyed this sort of content, I'm currently working on a Nintendo 64 game from scratch, and I'm making technical devlog videos just like this one explaining the full development process. If that's your thing, well, I have a playlist available here. It's been a while since I worked on that project for a bunch of reasons, but as of releasing this networking library, I'm going to be dedicating full time to my platformer project. Hopefully, a new update video will be coming out soon. Thanks for watching and have a good one.